This is a video about Archimedes' principle. So if you have an object, let me sketch one here for you, that's hanging from a string, then you're going to have a weight that the object's pulling down. You're going to have a tension in the string. Conversely, if you're in a situation where you have, let's say, a cup of water or some water, liquid here, I'm going to say pure water, and the object is submerged in the liquid, then the object's still going to have a weight pulling it down, force due to gravity. There's going to be a tension in the string, but as we talked about in class, there's an additional force, which we call the buoyancy force, which Archimedes said is equal to the weight of the displaced liquid. In this case, it's the displaced water. So if you can imagine water that has the same volume as the volume of the object here, that amount is pushed aside by the object. So that amount of water is how much lighter the object feels. So that's how much lower the tension here is when the object's submerged in the water. So I'm going to call this first tension Ft. I'm going to call the second tension actually Ft prime to distinguish it from the first tension. So this is the tension of the object, same object as in the first case, but when it's in water. So it feels lighter. So many of you might experience that when you put an object in water. It's going to seem lighter to you, including yourself. Okay, so new slide. So what does this mean as far as calculation of the density? Because that's really what Archimedes' principle allows us to do. Well, let's see what Ft in the first case is equal to the weight, or Fg. The second case, Ft prime, is equal to the weight minus the buoyancy force. And the reason I know each of these is because of Newton's second law. There's no acceleration on the object, so if you work out Newton's second law, this will be the case. So what I want to show you, I'll go to a new slide here, is that if you were able to take the weight of the object, that is Fg, and divide it by the buoyancy force the object experiences in the water, that's Fb, that's going to be equal to the density of the object times the volume of the object times g, divide that by the density of water times the volume of the object times g. And you might say, where did this all come from? Well, the top here, this first part, that's equal to the mass of the object. So all I'm saying is that the weight is equal to the mass of the object times g, so that's nothing you don't know. On the bottom, the object's displacing an amount of water equal to its volume. So the mass of the water that the object displaces is equal simply to the density of the water times the volume of the object, which is the same volume here. Alright, so if you cancel out like terms, the v's go away, the g's go away. So what's left is that the density of water density of the object divided by the density of water is equal to the weight of the object divided by the buoyancy force. So to simplify, Fg divided by Fb is equal to density of the object divided by the density of water. So you might ask, what does that buy us? What is knowing the density of the object divided by the density of the water really buy us? Well, the density of the object divided by the density of water is something known as specific gravity, which I'll abbreviate Sg. It basically gives the ratio of the density of the object to the density of water. Now, if you remember that the density of water is either 1,000 kilograms per cubic meter or 1 gram per cubic centimeter, then this ratio basically gives you a unitless representation of the density of the object. So in other words, if the density of the object is 3 grams per cubic centimeter, then its specific gravity is 3. If its specific gravity is 10, then the density is 10 grams per cubic centimeter, or 10,000 kilograms per cubic meter. So this ratio here essentially gives you the density. That's really helpful to know. All right, so how do we get this ratio? Well, as I mentioned in the previous slide, the ratio of the weight of the object the buoyancy force, if you can find that, is equal to the density of the object divided by the density of water, which is the specific gravity from which you can get the density. So how do you get this term? Well, if you weigh the object in the air, you get that. So if you have a hanging scale and you weigh the object from the air, you get Fg. If you weigh the object in the air and you subtract from it the weight of the object, or the tension in the string for the object when it's suspended in the water, you get Ft from an earlier slide minus Ft prime. Let's see what that's equal to. So in other words, Ft is the weight of the object, and Ft prime, you could say, is the apparent weight. It's how heavy the object appears to be when it's suspended in the water. So from that earlier, if you remember, we had that Ft prime is equal to Fg minus Fb. So if we now take Ft, subtract Ft prime from it, since Ft is just equal to the weight, we have Fg minus Fb equals Fb. So the difference between the two tensions is the buoyancy force. So what that means is that if you want to find the density of an object, what you can do is you weigh the object in water. Weigh the object in the air. It's going to give you the tension force here, which is equal to the weight. Then weigh it in water. Then take Ft, which is the weight, divide it by Ft minus Ft prime, and you will get Fg over Fb, which is equal to the density of the object divided by the density of water, which essentially is the density of the object. All you have to do is add units, and you got the density of the object. Okay, hopefully this will help you for Archimedes' principle.